Before computers existed, humans were already obsessed with sorting. Librarians spent their entire careers alphabetizing index cards by hand. Census workers in the 1890s literally shuffled millions of punch cards to count populations. For example, Herman Hollerith, the guy who got so tired of manually sorting census data that he invented punch card machines in 1889. His company. It eventually became IBM. One sorting problem literally birthed the computer industry. When the first computers arrived in the 1940s, they spent up to 25% of their processing time just sorting things. These room-sized machines that cost millions were basically very expensive filing cabinets. And if you dropped your sorted deck of punch cards, you just ruined your entire week. This is why programmers back then had trust issues. The first sorting methods were brutally simple because computer memory was more precious than gold. We're talking about machines with less memory than the modern calculator. Programmers had to be creative, which usually meant being incredibly inefficient. Take the story of the ENIAC computer in 1946. This beast weighed 30 tons and filled an entire room. But when they needed to sort a list of numbers, they basically had to teach it to count on its fingers. The programmers would manually rewire the machine for different operations. Sorting 100 numbers could take hours of preparation and minutes of actual computation. But the real nightmare was debugging. Imagine your sorting algorithm has a bug, but to fix it, you need to physically rewire a room-sized computer. Grace Hopper, one of the first computer programmers, literally found a moth stuck in the circuits of Harvard's Mark II computer in 1947. She taped the bug into her logbook and wrote first actual case of bug being found. This is where we get the term computer bug, and it happened while working on sorting problems. The magnetic drum storage systems of the 1950s made things even weirder. These drums spun at constant speed, and accessing data depended on where the read head was positioned. Sorting algorithms had to account for physical rotation timing. You couldn't just grab any piece of data. You had to wait for the drum to spin to the right position. Programmers developed optimized sorting algorithms that were essentially choreographed to the rhythm of spinning metal drums. Here's something nobody talks about. The first sorting algorithms were often classified military secrets. During World War II and the early Cold War, efficient data sorting was considered strategically important. The ability to quickly process radar data, decode messages, or analyze intelligence could determine the outcome of battles. Some of the most brilliant sorting innovations were locked away in government labs for decades. The transition from punch cards to magnetic tape in the late 1950s created a whole new category of sorting nightmares. Imagine trying to sort data when you can only read it sequentially, like a cassette tape. You couldn't jump to the middle of your dataset. You had to wind through everything in order. This led to elaborate multipass sorting algorithms, where data would be read from one tape, partially sorted, written to another tape, then read back again. Some complex sorts required dozens of tape drives working in coordination. But perhaps the most absurd part of early computer sorting was the human element. In the 1950s, it was common to have rooms full of people manually preparing data for computer sorting. They would sit at desks, transcribing information onto punch cards in the exact order the computer needed. These data preparation operators were essentially human preprocessors for sorting algorithms. The IBM 701 computer, released in 1952, came with a sorting routine that was considered so sophisticated that IBM charged extra for it. Companies had to literally buy their sorting capabilities separately. Imagine buying a car and having to pay extra for the ability to go in reverse. And here's the kicker. Most of these early sorting programs were one-shot deals. If you wanted to sort numbers instead of names, you needed a completely different program. If you wanted to sort in descending order instead of ascending, that was another program. The concept of a general-purpose sorting algorithm that could handle different data types and sort orders was still years away. The programmers of this era were basically digital archaeologists, working with machines that had no operating systems, no compilers, and no debuggers. They wrote sorting algorithms directly in machine code, often working through the night, because computer time was so expensive that most programming happened during off hours. IBM's sorting subroutines in the 1950s came with documentation that read like military manuals. Instructions like load accumulator with address of first record, execute comparison loop, branch on condition code. There were no variables named left pointer or right pointer. Everything was memory addresses and register numbers. A simple bubble sort implementation could span hundreds of lines of assembly code. The real breakthrough came when programmers realized they could generalize sorting operations. Instead of writing a new program for every type of data, they could write one program that accepted parameters. This seems obvious now, but in the 1950s, this was revolutionary thinking. The first parameterized sorting routines were considered marvels of engineering sophistication. But even these advanced systems had ridiculous limitations. Early sorting programs often had hard-coded maximum array sizes. Want to sort more than 1,000 items? Too bad. Rewrite the entire program. The concept of dynamic memory allocation was still decades away, so programmers had to predict the maximum amount of data they might ever need to sort. The Mercury delay line memory systems used in computers, like UNIVAC, made sorting even more bizarre. Data was stored as acoustic waves traveling through tubes of mercury. To access your data, you literally had to wait for the sound waves to propagate through liquid metal. Sorting algorithms had to be timed to the microsecond to avoid losing data in the mercury tubes. And then there were the paper tape systems. Imagine debugging a sorting algorithm when your data storage medium can literally catch fire. Paper tape was highly flammable, and computer rooms had strict no-smoking policies because a single cigarette could destroy weeks of work. Programmers developed paranoid backup habits, making multiple copies of their sorting programs on different color paper tapes. The most expensive part of computing in the 1950s wasn't the hardware, it was the mistakes. A single bug in a sorting program could waste hours of computer time that cost more than most people's annual salary. This economic pressure created a culture of obsessive code review and testing that modern programmers would find suffocating. But out of this chaos and inefficiency came something beautiful, the first real understanding of algorithmic complexity. When every CPU cycle costs money and every byte of memory is precious, you start to think very carefully about efficiency. The programmers of the 1950s didn't just write sorting algorithms. They invented the mathematical framework for analyzing why some algorithms were better than others. So what did these early programmers actually create? The first real sorting algorithm that most people learned was bubble sort, and it was immediately obvious that it was terrible. But terrible in an educational way, like learning to drive in a parking lot full of traffic cones. Bubble sort got its name from the way smaller elements bubble to the top of the list, like air bubbles rising in water. The algorithm compares adjacent elements and swaps them if they're out of order, then repeats this process over and over until no more swaps are needed. It's conceptually simple, which is why it became the first algorithm taught in computer science classes everywhere. But here's the brutal truth about bubble sort. It's catastrophically inefficient. To sort a list of 100 items, bubble sort makes nearly 5,000 comparisons in the worst case. To sort 1,000 items, it makes almost 500,000 comparisons. The performance scales so badly that sorting your iTunes library with bubble sort would take longer than actually listening to all the songs. The algorithm is so notoriously slow that it's become a punchline in programming circles. Barack Obama famously demonstrated his computer science knowledge during a 2007 Google interview by saying he knew that the bubble sort would be the wrong way to go for sorting 1 million items. Even presidents know bubble sort is garbage. Yet bubble sort refuses to die. Every computer science textbook starts with it. Every programming bootcamp teaches it first, and every job interview mentions it. Why? Because it's the perfect example of how not to solve a problem efficiently. It's the algorithmic equivalent of touching a hot stove. Everyone needs to experience the pain once to truly understand why it's bad. The man most commonly credited with formalizing bubble sort was actually trying to improve it. In 1956, Edward Harry Friend described the algorithm in a paper, but he was already suggesting optimizations. The irony is that bubble sort became famous precisely because Friend was trying to make it less terrible. Here's a fun fact. Bubble sort has dozens of variations with equally ridiculous names. There's cocktail sort, which bubbles in both directions. There's comb sort, which compares elements that are farther apart. There's even gnome sort, which was supposedly inspired by how garden gnomes sort flower pots. The fact that people kept trying to fix bubble sort instead of abandoning it entirely shows how attached programmers get to their first algorithmic love, no matter how dysfunctional. But let's talk about an algorithm that's only slightly less embarrassing: selection sort. If bubble sort is like frantically rearranging your bookshelf by swapping adjacent books, selection sort is like methodically finding the smallest book and putting it at the beginning, then finding the second smallest, and so on. Selection sort was actually one of the first algorithms that felt algorithmic to early programmers. It had a clear strategy: find the minimum element in the unsorted portion of the array, swap it with the first element, then repeat with the rest of the array. It was predictable, easy to understand, and still painfully slow. The weird thing about selection sort is that it's completely indifferent to the initial order of your data. Whether your list is already sorted, completely random, or sorted in reverse, selection sort makes exactly the same number of comparisons. It's like that friend who always takes the same amount of time to get ready, whether they're going to the grocery store or to a wedding. This predictability made selection sort popular in early computer systems where consistency mattered more than speed. If you knew your sorting routine would always take exactly the same amount of time, you could plan around it. But as datasets grew larger, this predictable slowness became predictably unacceptable. The origins of selection sort are murky, but it seems to have emerged independently in multiple places during the late 1950s. It was so obvious that several programmers probably looked at bubble sort and thought, there has to be a less stupid way to do this. Selection sort was their answer, still stupid, but less frantically so. Then came the algorithm that actually made sense: insertion sort. This one mimics how humans naturally sort things, like arranging a hand of playing cards. You pick up each new card and slide it into its proper place among the cards you've already sorted. Insertion sort was revolutionary because it was adaptive. If your data was already mostly sorted, insertion sort would finish quickly. If your data was completely random, it would still work, just more slowly. This was the first sorting algorithm that seemed to understand context. The algorithm was independently discovered multiple times in the early days of computing. Programmers would naturally gravitate toward this approach because it matched human intuition. You didn't need a computer science degree to understand insertion sort. You just needed to have organized a deck of cards at some point in your life. What made insertion sort special was its performance on small datasets. For lists of fewer than 10 or 20 elements, insertion sort was actually faster than more sophisticated algorithms because it had less overhead. This discovery would become crucial decades later when programmers realized they could use insertion sort as a subroutine in more complex algorithms. The first published description of insertion sort appeared in 1959 in a paper by computer scientist John Mauchly. But Mauchly wasn't presenting it as a new invention. He was describing it as something that everyone already knows. This casual attitude toward insertion sort reveals how intuitive the algorithm was to early programmers. But here's where things get interesting. These three algorithms, bubble, selection, and insertion sort, became the holy trinity of terrible sorting. Every programmer learned them, every computer science textbook taught them, and every performance-conscious developer avoided them like the plague in real applications. The educational value of these simple algorithms cannot be overstated. They taught an entire generation of programmers about the relationship between algorithm design and performance. When you've watched bubble sort struggle through a list of 1,000 items, making nearly 500,000 comparisons, you develop a visceral appreciation for efficiency. These algorithms also established the vocabulary we still use today. Terms like comparison, swap, stable sort, and in-place sorting all emerged from discussions of these basic algorithms. They created the conceptual framework that would later support much more sophisticated sorting methods. The tragedy of these early algorithms is that they were so easy to understand and implement that many programmers never bothered learning anything better. Well into the 1970s and 1980s, commercial software was still using bubble sort and selection sort for tasks that should have required more efficient methods. The simplicity that made these algorithms great for teaching made them terrible for real-world performance. By the early 1960s, programmers were getting fed up with sorting algorithms that took forever to finish. Computer hardware was getting faster, but datasets were growing even faster. The naive algorithms were hitting a wall, and something had to change. Enter the efficiency revolution. The breakthrough came from an unexpected place. The divide-and-conquer strategy borrowed from military tactics. Instead of trying to sort everything at once, what if you split the problem in half, solved each half separately, then combined the results? This thinking led to merge sort, the first sorting algorithm that didn't suck. Merge sort was invented by John von Neumann in 1945, but it took nearly 2 decades for programmers to fully appreciate its genius. Von Neumann was working on the EDVAC computer and needed a way to sort data stored on magnetic tape. The sequential nature of tape storage actually inspired the algorithm's design. You could split data across multiple tapes, sort each tape separately, then merge them back together. Here's what makes merge sort brilliant. It always makes the same number of comparisons regardless of the input. Whether your data is random, already sorted, or completely backwards, merge sort will take roughly the same amount of time. For 1,000 items, while bubble sort might make 500,000 comparisons, merge sort makes only about 10,000. It's not just faster, it's in a completely different performance category. The algorithm works by recursively dividing the array in half until you have individual elements, then merging these elements back together in sorted order. The merge step is where the magic happens. Combining 2 sorted lists into 1 sorted list is surprisingly efficient when done correctly. But merge sort had a problem that made early programmers nervous. It required extra memory. In an era when memory was expensive and scarce, doubling your memory usage to sort data seemed wasteful. Many programmers stuck with the slower in-place algorithms rather than pay the memory cost. This tension between time and space complexity would define decades of algorithmic development. The real game changer came in 1960 when Tony Hoare, a young British computer scientist, invented quicksort. Hoare was working on a machine translation project, trying to translate Russian scientific papers into English. He needed to sort words efficiently, and the existing algorithms were too slow for practical use. Quicksort uses a different divide-and-conquer approach. Instead of splitting the array in half arbitrarily, it chooses a pivot element and partitions the array so that all elements smaller than the pivot come before it, and all larger elements come after. Then it recursively sorts the 2 partitions. What makes quicksort special is its performance on random data. In the average case, it's one of the fastest comparison-based sorting algorithms ever invented. It typically outperforms merge sort because it has better cache locality and lower overhead. Quicksort became the default sorting algorithm in many programming languages and remains popular today. But quicksort has a dark secret. It has terrible worst-case performance. If you consistently choose bad pivots, quicksort degrades to the same performance as bubble sort. This happens when the data is already sorted or reverse sorted, which ironically are the cases where you'd most want good performance. Hoare's original paper on quicksort is fascinating because he immediately recognized this weakness. He spent considerable effort analyzing different pivot selection strategies and suggested several optimizations. The median of 3, pivot selection, where you choose the median of the first, middle, and last elements, became standard practice. The story of quicksort's adoption reveals how algorithmic innovation spreads through the programming community. Hoare presented the algorithm at a conference in 1961, but it took years for programmers to fully understand its implications. Early implementations were often buggy because the partitioning logic is trickier than it first appears. One of the most famous quicksort bugs occurred in a widely used library where the algorithm would fail catastrophically on certain inputs. The bug wasn't discovered for years because it only manifested on very specific data patterns. When it was finally found, it had been causing mysterious crashes in software around the world. This incident led to much more rigorous testing of sorting algorithms. Around the same time, computer scientists were developing heap sort, an algorithm based on the binary heap data structure. Heap sort was invented by J.W.J. Williams in 1964 as part of his work on the heap sort algorithm. It offered something neither merge sort nor quick sort could, guaranteed good performance, without extra memory usage. A binary heap is a complete binary tree where each parent node is larger than its children. This property makes it easy to extract the maximum element repeatedly, which is exactly what you need for sorting. Heap sort builds a heap from the input data, then repeatedly extracts the maximum element to build the sorted array. What makes heap sort interesting is its reliability. It always runs in the same time complexity regardless of input, like merge sort, but it doesn't require extra memory, like quick sort. However, in practice, heap sort is usually slower than quick sort on average cases because it has poor cache locality and more overhead. The development of these three algorithms, merge sort, quick sort, and heap sort, represented a fundamental shift in how programmers thought about efficiency. For the first time, there were algorithms that could handle large datasets in reasonable time. A list of 100,000 items that would take hours with bubble sort could be sorted in seconds with quick sort. This efficiency revolution also introduced the mathematical analysis of algorithms. Computer scientists began using big O notation to describe algorithm performance formally. The difference between O and superscript 2, algorithms like bubble sort and O, and log n, algorithms like merge sort wasn't just academic. It meant the difference between practical and impractical solutions. But perhaps the most important contribution of this era was the realization that there's no single best sorting algorithm. Merge sort is reliable and stable, but uses extra memory. Quick sort is fast on average, but has poor worst-case performance. Heap sort is consistent and in place, but has overhead. The choice depends on your specific requirements, data characteristics, and constraints. This insight led to a more nuanced understanding of algorithm design. Instead of seeking the one true sorting algorithm, programmers began building adaptive systems that could choose the best algorithm for each situation. This thinking would eventually lead to hybrid algorithms that combine multiple approaches for optimal performance across different scenarios. While mainstream programmers were obsessing over comparison-based sorting algorithms, a few rebels were asking a different question. What if we don't need to compare elements at all? This led to some of the most bizarre and specialized sorting algorithms ever invented. The first breakthrough came with counting sort, which throws the entire concept of comparison out the window. Instead of comparing elements to determine their order, counting sort literally counts how many times each value appears, then reconstructs the sorted array from these counts. It's like taking inventory of your sock drawer instead of arranging the socks directly. Counting sort only works when you know the range of possible values ahead of time. If you're sorting test scores from 0 to 100, counting sort can handle 1,000,000 scores in linear time. But if you're sorting arbitrary numbers, you're out of luck. This limitation made counting sort seem like a parlor trick rather than a practical algorithm. But the idea of non-comparison sorting opened floodgates. Computer scientists realized that when you have extra information about your data, you can sometimes break the theoretical lower bound that limits comparison-based algorithms. This insight led to an entire family of specialized sorting algorithms. Radix sort became the poster child for this approach. Instead of comparing entire numbers, radix sort examines individual digits, sorting the data multiple times based on each digit position. It's like organizing a filing cabinet by sorting first by the last digit, then the second to last digit, and so on. The history of radix sort goes back to the 1920s, long before computers existed. Hermann Hollerith's tabulating machines used a mechanical form of radix sorting to process census data. Workers would literally sort punch cards using mechanical sorters that read individual card columns. The algorithm was so effective that it survived the transition from mechanical to electronic computers, virtually unchanged. What makes radix sort fascinating is its performance on large datasets. While quick sort might make millions of comparisons to sort 1,000,000 integers, radix sort can finish the job by examining each number only a few times. For certain types of data, it's impossibly fast compared to comparison-based algorithms. But radix sort has weird limitations. It works great for integers, but sorting floating-point numbers requires careful handling of signs and exponents. Sorting strings is possible but complicated. The algorithm is fast but inflexible, which limited its adoption in general-purpose programming languages. Then there's bucket sort, which takes a completely different approach. Instead of sorting the entire dataset at once, bucket sort distributes elements into multiple buckets, sorts each bucket individually, then concatenates the results. It's like organizing a messy room by throwing similar items into different boxes, then organizing each box separately. Bucket sort's performance depends entirely on how evenly the data is distributed across buckets. With uniform data, it can achieve linear time performance. With skewed data, it degrades to whatever algorithm you use to sort individual buckets. This variability made bucket sort popular in specialized applications, but rare in general-purpose libraries. The 1980s brought us some truly exotic algorithms that pushed the boundaries of what sorting could be. Pancake sort, invented by Bill Gates and Christos Papadimitriou in 1979, can only reverse prefixes of the array. The algorithm is named after the problem of sorting a stack of pancakes using only a spatula. You can flip the top portion of the stack, but you can't rearrange individual pancakes. Pancake sort is mathematically interesting, but practically useless. It requires up to 2n operations to sort n elements, making it slower than even bubble sort. But it spawned an entire subfield of research into sorting with restricted operations. Mathematicians discovered that the minimum number of pancake flips needed to sort any arrangement is surprisingly difficult to calculate. The crown jewel of terrible sorting algorithms has to be BOGO sort, also known as stupid sort or monkey sort. The algorithm is beautifully simple. Randomly shuffle the array, check if it's sorted, and if not, shuffle again. Repeat until sorted. BOGO sort is so inefficient that its average running time is factorial. For just 10 elements, you might need to try over 3 million random arrangements. For 13 elements, you're looking at over 6 billion attempts on average. But here's the thing. BOGO sort might get lucky and finish immediately, or it might run forever. The uncertainty is both hilarious and terrifying. The algorithm was first described in a 1986 humor column, but it quickly became a teaching tool for explaining why randomized algorithms need careful analysis. BOGO sort demonstrates that just because an algorithm is simple doesn't mean it's good. Sometimes simple is simply stupid, but the rabbit hole goes deeper. Sleep sort, discovered in 2011 on an internet forum, sorts numbers by creating a separate thread for each element, then making each thread sleep for a duration equal to its value. The threads wake up in sorted order, creating a sorted list as a side effect of concurrent programming. Sleep sort is simultaneously brilliant and idiotic. It achieves max input time complexity, which can be better than comparison-based algorithms for small, bounded integers. But it requires as many threads as input elements, making it impractical for large datasets. It also depends on the operating system's thread scheduler being perfectly fair, which is never guaranteed. The algorithm became an internet meme because it's such an elegant abuse of threading primitives. Programmers began creating variations like network sort, which sends each element to a remote server that delays responses based on the value, and GPU sort, which uses graphics hardware to perform the delays in parallel. Spaghetti sort takes the concept even further into absurdity. The algorithm involves cutting pieces of spaghetti to lengths proportional to the input values, then dropping them vertically and picking them up in order from shortest to longest. It's O-N. Time complexity if you don't count the time needed to cut spaghetti or the precision required to measure lengths. These joke algorithms serve an important purpose. They force programmers to think about the assumptions underlying traditional sorting. Why do we assume that comparison is the only way to determine order? What if we had infinite parallel processors? What if we could manipulate physical objects instead of abstract data? But perhaps the most mind-bending sorting algorithm is quantum BOGO sort. This theoretical algorithm uses quantum superposition to try all possible arrangements simultaneously, then measures the quantum state to collapse it to the sorted arrangement. In theory, it sorts any array in O(1) time using quantum mechanics. Quantum BOGO sort doesn't actually work with current quantum computers, but it illustrates how exotic computing models might change our understanding of fundamental problems. As quantum computing develops, We might discover that some problems we consider computationally hard are actually easy in quantum systems. The study of exotic sorting algorithms reveals something important about computer science. The boundary between practical and impractical is constantly shifting. Algorithms that seem ridiculous today might become useful as hardware evolves. The sorting algorithms of tomorrow might be just as strange as sleep sort seems today. By the 1990s, computer scientists had a sobering realization. They'd been living a lie. All those elegant algorithms they'd spent decades perfecting, they worked great on random data in academic papers. But real-world data had patterns, and those patterns broke everything. The problem was that most sorting algorithms were designed for worst-case scenarios that rarely happened in practice. Quicksort was lightning fast on random data, but choked on sorted inputs. Merge sort was reliable but wasted memory. Heap sort was consistent but slow. What programmers needed wasn't another pure algorithm. They needed algorithms that could adapt to different situations. Enter Tim Peters, a Python developer who got tired of the language's mediocre sorting performance. In 2002, Peters created TimSort, named after himself with characteristic programmer ego. But unlike most vanity algorithms, TimSort actually deserved the attention. TimSort is a hybrid algorithm that combines merge sort with insertion sort. But the genius is in how it detects and exploits patterns in real-world data. Instead of treating all data as random chaos, TimSort looks for runs, sequences that are already in order or reverse order. When it finds these patterns, it uses them as building blocks for efficient merging. The algorithm starts by scanning the input for natural runs of sorted data. If it finds a run in reverse order, it reverses it. If runs are too short, it extends them using insertion sort. Then it merges these runs using a sophisticated strategy that maintains stability while minimizing memory usage. What makes TimSort revolutionary is its real-world performance. On completely random data, it performs about as well as traditional merge sort. But on data with patterns, which describes most real datasets, TimSort can be dramatically faster. Sorting an already sorted array takes linear time instead of the n log n time required by traditional algorithms. Peters' innovation wasn't just technical, it was philosophical. He rejected the academic obsession with worst-case performance and focused on making the common cases fast. TimSort assumes that real data has structure and exploits that structure aggressively. The algorithm became Python's default sort in version 2.3 and was so successful that Java adopted it in 2012. When Oracle replaced their merge sort implementation with TimSort, some Java programs became noticeably faster without any code changes. That's the mark of a truly superior algorithm. It makes existing code better automatically. But TimSort wasn't the only hybrid approach gaining popularity. Around the same time, the C++ standard library adopted IntroSort, invented by David Musser in 1997. IntroSort stands for introspective sort, and it's essentially quicksort with a backup plan. The algorithm starts with quicksort, but it monitors its own performance. If the recursion depth gets too deep, indicating that quicksort is hitting its worst-case behavior, IntroSort switches to heap sort to guarantee good performance. For small subarrays, it switches to insertion sort for efficiency. This kind of algorithmic self-awareness was revolutionary. Instead of hoping that the worst case wouldn't happen, IntroSort actively detects when it's happening and adapts accordingly. The result is an algorithm with quicksort's average case speed and heap sort's worst-case guarantees. IntroSort became the default sort for C++ SSTD sort function, meaning that millions of C++ programs use it without knowing it exists. The algorithm is so transparent that most programmers never realize they're using a hybrid approach. They just know that STD sort is fast and reliable. The success of these hybrid algorithms sparked a renaissance in sorting research. Computer scientists began developing increasingly sophisticated adaptive algorithms that could handle multiple types of patterns and pathologies. Library sort, invented by Michael Bender in 2004, takes inspiration from how librarians insert new books into sorted shelves. Instead of shifting every book to make room for a new one, librarians leave gaps on shelves to accommodate future insertions. Library sort applies the same principle to array sorting. The algorithm maintains a sorted array with gaps, inserting new elements into appropriate positions. When gaps fill up, it reorganizes sections of the array to create new gaps. The result is an algorithm that can be faster than traditional methods on certain types of input data. Spread Sort, developed by Stephen Ross in 2007, combines the best aspects of comparison-based and non-comparison sorting. It uses a hybrid approach that switches between radix-style distribution and comparison-based sorting, depending on the characteristics of the data being sorted. The algorithm analyzes the input data to determine the most efficient approach. For integers with limited ranges, it uses radix-style sorting. For strings, it uses a specialized string sorting algorithm. For floating-point numbers, it handles the bit representation carefully to maintain numerical order. What makes Spread Sort interesting is its focus on real-world performance across different data types. Instead of being optimal for one specific type of input, it tries to be very good for all common types of input. This pragmatic approach reflects the modern understanding that general-purpose algorithms need to handle diverse data efficiently. The multi-core revolution of the 2000s brought new challenges to sorting. Traditional algorithms were designed for single-threaded execution, but modern computers had multiple CPU cores sitting idle during sorting operations. This led to the development of parallel sorting algorithms that could utilize multiple cores simultaneously. Sample sort became one of the most successful parallel sorting approaches. The algorithm divides the input among multiple processors, has each processor sort its portion independently, then merges the results. The key innovation is the sampling phase, where processors examine random elements to determine good splitting points for load balancing. The challenge with parallel sorting isn't just dividing the work. It's ensuring that processors don't interfere with each other and that the final merge step doesn't become a bottleneck. Sample sort addresses these issues through careful load balancing and hierarchical merging strategies. But perhaps the most significant development in modern sorting is the recognition that different algorithms excel in different contexts. This led to the development of adaptive frameworks that can choose the best algorithm for each specific situation. Modern sorting libraries often include decision trees that analyze input characteristics and select appropriate algorithms automatically. They might use counting sort for small integer ranges, radix sort for large integer datasets, tim sort for data with patterns, and intro sort for general-purpose sorting. This algorithmic pluralism represents a maturation of the field. Instead of seeking the one true sorting algorithm, modern computer scientists embrace the reality that different problems require different solutions. The best sorting algorithm is the one that's best for your specific use case, and the smartest approach is often to let the computer decide which algorithm to use. Here's the dirty secret about sorting algorithms. Most programmers never implement them from scratch. They use whatever their programming language provides by default and pray it's fast enough. But behind the scenes, these algorithms are running the world, and when they fail, the consequences can be spectacular. Let's start with databases, where sorting is literally a matter of life and death for performance. Every time you run a SQL query with an order by clause, you're invoking decades of sorting research. Database engines like Oracle, PostgreSQL, and MySQL have entire teams dedicated to optimizing sorting performance because a slow sort can bring an entire application to its knees. The most famous database sorting disaster happened at Knight Capital in 2012. A deployment error caused their trading algorithms to use an inefficient sorting method for processing orders. In 45 minutes, the system made thousands of erroneous trades, losing the company $440 million. The company went bankrupt 4 days later. That's the most expensive sorting bug in history. Nearly $500 million lost because someone used the wrong algorithm. But databases face unique sorting challenges that textbooks never mention. When you're sorting terabytes of data that can't fit in memory, you need external sorting algorithms that use disk storage. These algorithms must minimize disk I/O operations because accessing disk is thousands of times slower than accessing memory. Modern database systems use sophisticated external merge sorts that can handle datasets larger than available memory. They create sorted runs that fit in memory, write these runs to disk, then merge them back together. The engineering challenge isn't just algorithmic, It's about managing disk bandwidth, predicting access patterns, and coordinating multiple storage devices. Search engines like Google and Bing are essentially massive sorting operations. Every search query triggers multiple sorting operations, ranking web pages by relevance, sorting results by freshness, organizing ads by bit amounts. Google processes over 8 billion searches per day, meaning their sorting algorithms handle more operations in a single day than most programs handle in their entire lifetime. The PageRank algorithm that made Google famous is fundamentally a sorting problem. It computes important scores for billions of web pages, then sorts them to determine search result rankings. The scale is mind-boggling. Google's index contains hundreds of billions of web pages, and the sorting operations must complete in milliseconds to provide real-time search results. But here's where it gets interesting. Google doesn't use traditional sorting algorithms for PageRank. The scale is so massive that they've developed custom distributed sorting systems that run across thousands of computers simultaneously. These systems can sort datasets that would take traditional algorithms centuries to process. The gaming industry has its own sorting obsessions, particularly around graphics rendering. Every frame in a 3D game requires sorting thousands of polygons by depth to ensure proper visibility. With games running at 60 frames per second, graphics cards perform millions of sorting operations every second. This led to the development of specialized GPU sorting algorithms that exploit the parallel architecture of graphics hardware. Unlike CPU algorithms that process one element at a time, GPU sorting algorithms process thousands of elements simultaneously using hundreds of cores working in parallel. But the most ridiculous sorting performance requirements come from high-frequency trading. Financial firms spend millions of dollars to reduce network latency by microseconds, and sorting performance can directly impact profitability. Some trading algorithms sort incoming market data in real time, and the difference between a microsecond faster sort can mean the difference between profit and loss on a trade. This obsession with performance has led to some extreme optimization techniques. Trading firms use custom FPGA hardware that implements sorting algorithms directly in silicon. They optimize for specific data patterns that occur in financial markets. They even consider the physical distance between CPU cores when designing sorting algorithms, because the speed of light becomes performance constraint at these scales. The most entertaining sorting bugs usually involve unexpected data patterns. In 2019, a major e-commerce site had a bug where product search results were randomly ordered instead of sorted by relevance. The cause? Their sorting algorithm was using the memory address of product objects as a tiebreaker, and memory addresses are essentially random. Customers trying to find products by price or popularity were seeing completely chaotic results. Another classic bug occurred in a music streaming service, where playlist shuffling wasn't actually random. It was using a broken sorting algorithm that created subtle patterns. Users noticed that certain artists appeared too frequently in shuffled playlists. The fix required implementing a proper random shuffle algorithm, which is surprisingly tricky to get right. Operating systems use sorting algorithms for process scheduling, file system operations, and memory management. Every time you open a file dialog and see files listed alphabetically, that's a sorting algorithm at work. But OS-level sorting has unique constraints. It must be fast, use minimal memory, and never crash even with malicious input data. The Linux kernel includes multiple sorting implementations optimized for different use cases. There's a simple heap sort for situations where memory is extremely limited, a sophisticated intro sort for general-purpose sorting, and specialized algorithms for sorting network packets and disk I/O requests. One of the most critical sorting applications is in cryptography and security. Many cryptographic protocols require sorting random numbers or sorting encrypted data without revealing the underlying values. This has led to the development of oblivious sorting algorithms that hide data access patterns from potential attackers. These security-focused sorting algorithms are often much slower than traditional methods because they must avoid revealing information through timing or memory access patterns. But in security applications, correctness and privacy are more important than raw performance. The medical industry uses sorting algorithms for processing everything from DNA sequences to medical imaging data. Bioinformatics algorithms that analyze genetic data often spend most of their time sorting and searching through massive biological databases. A faster sorting algorithm can literally accelerate medical research and drug discovery. But perhaps the most unexpected place you'll find sorting algorithms is in artificial intelligence and machine learning. Training neural networks requires sorting training data, finding nearest neighbors in high-dimensional spaces, and ranking prediction confidence scores. As AI systems become more sophisticated, the sorting operations become more complex and performance-critical. Modern recommendation systems like those used by Netflix, Amazon, and Spotify are fundamentally massive sorting operations. They sort millions of items by predicted user preference scores, then present the top results as recommendations. The quality of these sorts directly impacts user satisfaction and business metrics. The future of sorting is heading in some surprising directions. Quantum computing might eventually make certain sorting problems trivial by allowing quantum algorithms to explore all possible arrangements simultaneously. DNA computing researchers have demonstrated sorting algorithms that use biological processes to organize data stored in genetic material. But for now, the humble sorting algorithm continues to run quietly in the background of almost every computer system, organizing our digital world one comparison at a time. From the simple bubble sort that taught us about algorithmic thinking to the sophisticated hybrid algorithms that power modern applications, sorting remains one of the most practical and influential areas of computer science. The next time your music playlist loads instantly, your search results appear in perfect relevance order, or your online shopping cart calculates shipping costs in milliseconds, remember that you're witnessing the culmination of decades of sorting algorithm research. Behind every smooth digital experience is an army of invisible algorithms, working tirelessly to keep our data organized and accessible.